Hello guys, I hope you all are doing good. I am Vaishali Khan and we are discussing the electronics engineering. Today in this video we are going to analyze the half wave rectifier. In the previous video also we had discussion about some of the parameters like the ripple factor, the form factor and the voltage regulation. Now today in this video we are going to talk about some another parameters. So we are going to wind up our discussion on the half wave rectifier in this video itself. So you have to watch this video very carefully with full of attention, and if you are finding anything which you must write in your formula notebook, you should write it. So a lot of things you are going to find in this video also. So let's start our discussion with the rectification or the power conversion efficiency. What is the power conversion efficiency? So I know in the rectification I am converting the AC input to the DC output. Now what is the power conversion? How much AC power is converted into the DC output? So we are dealing here with the powers. So what power I have supplied at the input, what DC output power I have got. So now rectification efficiency, or it is also known as the power conversion efficiency, is the ratio of output DC power at the load to the input AC power from the mains, right? So rectification efficiency is output DC power available at load upon input AC power from the mains. So in the terms of symbols, how I can represent it? Efficiency can be represented as eta in percentage. So because I am writing here in percentage, I will be having the multiplication of 100. Now here the output power in DC. So P output DC divided by P input AC. Right, what is the P output DC? The output power which is DC power available. So it would be equal to I DC square into RL. We know the formula of power which is I square into R. Right, here I am talking about the DC power. It is generated due to the DC current. So here I will be having I DC square. Now it is generated at the load resistance, so IDC square into RL, right? So what was IDC? The value of IDC was Im upon pi. So IDC square would be Im square upon pi square into RL, right? So I hope you understood how I computed the P output DC. Now coming to the P input AC. What is the input power that I was sending? I was sending the power which can be represented in the terms of IRMS. So if I multiply IRMS with all of the resistances, because the input power is going through all of the resistances. We talked about three resistances: the secondary resistance at the transformer, at the secondary winding of the transformer I was having some resistance which is very small. Then second, we talked about the forward resistance of the diode. Third, we talked about the load resistance. So IRMS square into RL plus RF plus R2, right? So I hope you understood this thing. What is IRMS? IRMS was Im upon 2. So what would be IRMS square? It would be Im square upon 4, which is multiplied with RL plus RF plus R2, right? So now I know what is PIAC. I know what is PODC. I have to just divide them. I have to find out the efficiency in percentage. I would be dividing P output DC by P input AC. So Im square upon pi square into RL is divided by Im square upon 4 RL plus RF plus R2 and multiplied with 100, so that I will get the efficiency in percentage. Right, so now here Im square and Im square will get cancelled out. I would be left out with 4 upon pi square. Now here RL would be as it is upon RL plus RF plus R2 into 100%. Right, so if you compute 4 upon pi square, you will be getting 0.4053, and when you multiply it with 100, you are going to get 40.53. Right, now in the denominator, I will be taking this RL in the denominator, and if I divide RL with this RL, I will be getting 1, and here we will be having RF plus R2 divided by RL, right? So 1 plus RF plus R2 divided by RL, and in the numerator we had already discussed 4 upon pi square will be equal to 0.4053 into 100. So the efficiency can be represented as 40.53 upon 1 plus RF plus R2 upon RL. Now I told you forward resistance, and the R2 is very small as compared to RL, so I can neglect it. So because very small term is divided by a very big term, like let's suppose 0.5 ohm is divided by 2000 ohm, I will be getting the negligible term over here. So this term can be neglected and I will be getting the efficiency is equal to 40.53%. So the power conversion efficiency, the how much power from AC is converted to DC for half wave rectifier is 40.53 theoretically. This is the theoretical value, and practically it is even less than that, right? So now coming to the transformer utilization factor or TUF. What is TUF? So transformer utilization factor is represented as output DC power available at the load divided by the power rating of the transformer, right? So what is the output DC power that we have divided by what is the power rating of the transformer that I was using? I was using a step down transformer. What was the power rating of the transformer? Now the volt ampere rating of the transformer can be represented in VRMS into IRMS because the transformer was dealing with the AC voltage and AC current, so it can be represented as VRMS into IRMS. Here VRMS will be equal to VM upon root 2 and IRMS will be equal to IM upon 2, right? So now you can see VRMS I have taken for the full cycle because the voltage at the secondary of the transformer will be available for the full cycle, and this is the reason VRMS is represented as VM upon root 2 whereas IRMS is represented as IM upon 2. So volt ampere rating of the transformer can be represented as IM square upon 2 root 2 multiplied with RL plus RF plus R2. So how did it come? So the volt ampere rating will be equal to VRMS into IRMS, right? So now VRMS can be represented as I into R. So what is the R over here? The total R is RL plus RF plus R2. So now this is how I can represent VRMS into the terms of IRMS. VRMS is equal to IRMS into RL plus RF plus R2. So now VRMS is equal to IRMS like this, and in the VRMS in the denominator I had root 2, for IRMS I had the 2 in the denominator. So now how I can represent the volt ampere rating of the transformer? It can be represented as IM square RL plus RF plus R2 upon 2 root 2. So this is how we can represent the volt ampere rating of the transformer. Now output DC, I hope you remember it was represented as IM square RL upon pi square. This we had already computed, right, in the previous case. So if I divide this thing by this thing, so I can take this as a reciprocal and I can multiply it. So IM square RL upon pi square is multiplied with 2 root 2 upon IM square RL plus RF plus R2. So IM square will get cancelled out. We will be having 2 root 2 upon pi square, and this RL will go here in the denominator. We are left out with RL upon RL, which is 1 plus RF plus R2 upon RL, right? So this factor is very small. Again, it can be neglected because RL is much greater than RF plus R2. So now what would be my transformer utilization factor? It would be 2 root 2 upon pi square, which is 0.287. In the percentage, if I multiply it with 100, I will be getting in the percentage. So transformer utilization factor in percentage will be 28.7%. I hope you understood this thing. Now coming to the peak inverse voltage. What is PIV? What is the peak inverse voltage? The maximum voltage that appears across the diode during the non-conducting or off state. When the diode is in non-conducting state, it can be treated as an open circuit, right? We all know this thing. So now there would be some voltage that is coming at the diode because there would be no current, there would be no voltage at RL. Whatever voltage we have at the VM we will be having all of the voltage drop at the diode itself, right? So if I have Vi as the input voltage, Vm as the voltage which is coming at the secondary of the transformer, so now if I apply KVL in this circuit, so this is the voltage that we have to find out, the peak inverse voltage, because no current is flowing through RL, I is nearly equal to 0, only the leakage current is flowing. So now I will consider I is equal to 0, so the voltage across this diode in the reverse bias condition, the maximum voltage that can appear, that is V, is the peak inverse voltage. So maximum voltage that appears across the diode during non-conducting or off state is the peak inverse voltage. It is calculated when negative peak occurs at the secondary of the transformer due to the negative side of the sinusoidal wave it is coming, and the current in the circuit is nearly equal to 0. So here we will be having no voltage across the load resistance, because the current is 0, there would not be any voltage drop across RL. So if I apply KVL, Vm minus V, which is peak inverse voltage, is equal to 0. So Vm is equal to peak inverse voltage. Now what is the use of peak inverse voltage? It is used for selecting the diode ratings, which is the diode which I have to use for a particular application. If I use higher voltage than the peak inverse voltage, the diode will get burned out, right? So it does not exceed the diode's maximum reverse voltage withstand capability, otherwise the diode will get damaged, right? Now coming to the ripple frequency. So at the output, what I was getting pulsating voltage, right? I was not getting a DC voltage at the output. So the frequency of this output is the ripple frequency, right? What was the frequency of output? It was same as the sinusoidal wave that I have sent. So the ripple frequency is equal to Fs, the sinusoidal frequency that I have sent, equal to the frequency of supply voltage. Now coming to the disadvantages of half wave rectifier, and this is the reason we are moving towards the full wave rectifier. The first disadvantage is that it is having the low efficiency. I told you the efficiency is nearly equal to 40%, and that too the ideal efficiency practically it is even less than that. We have very high ripple factor, it was 1.21 in percentage, it will be equal to 121, ideally it should be 0. So the ripple factor is very high. Low transformer utilization factor, we already seen in this video only that the transformer utilization factor is 28%, which is very less. Now the low DC output voltage and current, the DC output voltage and current, again it is low, because for half wave it is nearly 0, right? The possibility of transformer core saturation due to the unidirectional current flow. So these are all of the disadvantages that we have for the half wave rectifier. So I hope you understood each and everything that I have discussed. You have prepared your notes. Now you have the formula sheet. If not, you can again prepare, go watch the video, stop at the places I was discussing about the formula and put it in your formula sheet. So I hope you understood each one of the thing. If you liked it, you can push the like button, subscribe to the channel, share it with your friends and give me your feedback. And if any query, you can go to the comments. Thank you so much.